This lecture video will introduce the idea of constructing a confidence interval in order to estimate a population parameter, and we'll begin by estimating population proportions. Here's the big idea. Consider an entire population. In most cases, it's very difficult to gain information about an entire population. So instead, we can select a subset of the population called a sample. With a manageable sample, we can calculate some useful information. And when we compute a proportion, mean, or standard deviation for this sample, that's called a statistic. And we could use this statistic to approximate a parameter. That is, we can use the statistic that we got from the sample to help us approximate a parameter that we can use to describe the population. For example, we see screens like this on Facebook or on the news all the time. This one's a few years old, back when Obama was president, but we have its approval rating of 41%. Now, this is implying that 41% of all Americans approve of how Obama is handling his job as president. But they certainly didn't ask me. They certainly didn't ask all 250 million of us, did they? No, they instead took a sample, and we can see at the bottom that they've given themselves some wiggle room, plus or minus 3%, and they've noted that they asked 1,000 adults. That was their sample. In other words, when they say that 41% of Americans approved of the president's job performance, they were taking a sample statistic to help them approximate a parameter to describe the entire population. In this case, the population is the United States, which is about 250 million people. It would be kind of ridiculous to try to ask all 250 million people just to have a 2-second screen on your news program. So they instead selected a sample, and in this case, their sample size was 1,000, a much more manageable amount of people to ask. From that, they computed a statistic. In this case, they found how many people out of the 1,000 approved of the president's job performance. Out of 1,000 people, this would be 410, or 41%. Finally, they can use that statistic of 41% to approximate the parameter for the population. They have 41%, give or take, or plus or minus 3%, which is equivalent to constructing the interval from 38% to 44%. Since 41 minus 3 is 38 and 41 plus 3 is 44. They're saying that based on this sample of 1,000 people, they would approximate the actual value for the entire population to be between 38% and 44%. This is exactly what we mean by a confidence interval. We don't expect the actual value of the parameter to be exactly the same as that of the statistic, but we do expect them to be relatively close together. This value of the statistic, the 41% that they got from the sample, is a sample proportion, which we notate by p hat. This is also considered the best point estimate for the population proportion. It's not the actual population proportion, but it is our best estimate based on our sample. And the result is this confidence interval for the population proportion, or the proportion of Americans that approve of the president's job performance. For the population proportion, we use a p without a hat. Let's continue to add to our vocabulary surrounding confidence intervals. We mentioned a proportion, but let's define it here. A proportion is the fraction of a group that belongs to a category of interest. When we have a sample proportion, we use a p hat, and for a population, we use a p. Point estimate is a single value that's used to approximate a population parameter. Proportion, mean, standard deviation, or variance. The sample proportion, p hat, is the best point estimate of the population proportion. We'll be using a sample proportion to help us build a confidence interval for the population proportion. So what exactly is a confidence interval? This is a range of values that is used to estimate the true value of a population parameter. With our previous example, we had a sample proportion equal to 41%, and we used that 41% as the center of our confidence interval. That plus or minus 3% is what we call the margin of error. If we go 3% above 41%, we find ourselves at 44%. And if we go 3% below 41%, we are at 38%. This creates an interval from 38 to 44% where we think the population parameter actually lives. We believe, based on the sample, that between 38 and 44% of Americans approve of the president's performance. We also have what's called a confidence level, and it's how confident we are that the population parameter is actually in the interval that we created. The three most common confidence levels are 90%, 95%, and 99%. Now that we have an idea of what a confidence interval is, let's start talking about how to create one for a population proportion. We've already discussed how we use a p for population proportion and a p hat for sample proportion. Q hat is equal to 1 minus p hat. Lowercase n is the number of sample values, or the sample size, and we use a capital E to notate the margin of error. In the example that we were just playing with, we had a sample proportion of 41%, or 0.41, which would make Q hat equal to 1 minus 0.41, or 0.59. The sample size was 1,000, so that's our lowercase n, and that plus or minus 3% was our margin of error, or 0.03. Whatever confidence level we are working with or striving to obtain, alpha is equal to 1 minus the confidence level. Picturing this on a normal distribution, our confidence level is in the center. And it won't be 100%. There will always be something left in the tails. And what's left over in those tails is precisely alpha. Alpha is 1 minus the confidence level, or everything that's left over in those tails. And if alpha is split between those two tails, that means that each tail contains half of alpha, or alpha over 2. We have half of alpha in the right tail and half of alpha in the left tail. The last detail we need to add is the idea of the z-score that separates the right tail, alpha over 2 portion, in the standard normal distribution. This z-score here we call z sub alpha over 2, and the corresponding z-score on the other side is negative z sub alpha over 2. Before we dive into an example for constructing a confidence interval, let's make sure we know how to find z sub alpha over 2 for a particular confidence level. Let's calculate z sub alpha over 2 for a 90% confidence interval. If we have a 90% confidence interval, that means that we have a confidence level of 90%, or 0.90. That means that alpha is equal to 1 minus 0.90, or 0.10. Adding those to our picture, we have 0.90, our confidence level, in the center, with 0.1 or 10% left in the tails. Dividing alpha by 2, we have 0.10 divided by 2, or 0.05. So we have alpha over 2, or 0.05, or 5% in each of the tails. What we are looking for is the z-score here. That's z sub alpha over 2. And it's what separates that right area of 0.05 from a left area of 0.95. We can find this z-score by either looking at our z-table or by using our calculator. Either way, we are looking for a z-score that has a left area of 0.95. Notice that to the left, we have this 90% plus another 5%, or a total of 95%. Looking at your z-table, you'll find that this z-score is right between 1.64 and 1.65. And averaging those values, we have a z-score of 1.645. You can also find this value using the INV norm function on your calculator. It would be a really good idea to repeat this exercise with the other two commonly used confidence levels. That way you have these z sub alpha over 2 values ready when you need them. We now have everything we need to be able to construct a confidence interval for a proportion. The basic idea of estimating a population proportion is creating a confidence interval that is centered around a sample proportion, p hat. And we'll add and subtract our margin of error to give us a range of values around this proportion. The margin of error in this case is calculated by finding z sub alpha over 2 and multiplying it by the square root of p hat times q hat divided by n. In other words, we could write this confidence interval as p hat plus or minus z sub alpha over 2 times the square root of p hat times q hat over n. This will result in an interval from p hat minus e to p hat plus e. When working this out using the formula, the first step is to calculate the sample proportion, p hat. The second step is to calculate the margin of error, capital E. And the third step is to create the interval from p hat minus E to p hat plus E. Now you might be wondering, can we also do this with our calculator? Yes, we can. The calculator function that we need is 1-prop z int. That stands for a one sample proportion z interval. There are 3 requirements for constructing a confidence interval like this. First, the sample must be a random sample. Second, this must be a binomial distribution, meaning that we do need to meet all of the requirements for binomial distribution. That's the idea of only 2 options, success and failure, and every trial has the same probability for success. Third, we need to have the products NP and NQ greater than or equal to 5. We are now ready for an example. In this example, we're told that in a survey of 1,002 people, 70% said that they voted in a recent presidential election. We're going to find a 99% confidence interval estimate of the proportion of people who say they voted, and we'll round to 3 decimal places. First, let's list out everything that we know. Our sample size is 1,002. Since 70% said that they voted in the presidential election, that's our p hat, the proportion of the sample. We'll write that as 0.70. That means that q hat, or 1 minus p hat, is 0.30. We want to construct a 99% confidence interval estimate. That means our confidence level is 99%, or 0.99. That only leaves 1% left over for alpha, or 0.01. And half of alpha, 0.01 divided by 2, is equal to 0.005. We're going to walk through this example, calculating the confidence interval by hand. In a next example, I'll show you how to use your calculator. We already have p hat, so the next step is to calculate E, the margin of error. This is equal to z sub alpha over 2 times the square root of p hat times q hat divided by n. We already have all of these values except for z sub alpha over 2. With our confidence level of 0.99 and only 0.005 left in each tail, those are our alpha over 2 values, z sub alpha over 2 is the z-score that has a left area of 0.995. Using your z-table or INV norm function, we find this z-score to be 2.575. So in our calculation for the margin of error, we have 2.575 times the square root of p hat 0.70 times q hat 0.30 divided by n, 1,002. Putting this into our calculators, we find that E is equal to 0.0373. Notice that I held on to one more decimal place than what I'm really going to need at the end. This will help make sure that I hang on to as much accuracy as possible and only round in the last step. The last thing we need to do is find p hat plus or minus E. In our case, that's 0.70 plus or minus 0.0373. 0.7 minus 0.0373 gives us 0.663. And 0.70 plus 0.0373 gives us 0.737. So we would estimate the population proportion to be somewhere between these two values. With our sample proportion of 70%, we estimate that the population proportion is between 66.3 and 73.7%. Let's talk about how we present these results. It's important that we give meaning to the results of these calculations rather than simply stating numbers. For this example, we found that the 99% confidence interval estimate of the population proportion P is the interval from 0.663 to 0.737. This is equivalent to saying that the population proportion is between 0.663 and 0.737. Either way that we write this, we are describing the same range of values. To state this answer as a complete sentence, we would say that we are 99% confident that the interval from 0.663 to 0.737 actually does contain the true value of the population proportion. We believe with 99% confidence that between 66.3 and 73.7% of people would say that they voted in the most recent election. Let's look at another example. In this example, we are told that in a Harris poll of 520 human resource professionals, 90% said that the appearance of a job applicant is most important for a good first impression. Before we construct our confidence interval, let's make sure we have a solid understanding of proportion. Among those 520 human resource professionals, how many of them said that the appearance of a job applicant is the most important for a good first impression? We are told that 90% of them said this, but if 520 were surveyed, then 90% of them is how many? We can find this by multiplying 0.9 times 520. That tells us that 468 out of the 520 said that appearance is the most important. Now let's construct a 99% confidence interval to estimate the proportion of all HR professionals. We'll round our final answer to 2 decimal places. As always, let's first list out everything that we know. Our sample size n is 520. Our sample proportion, p hat, is equal to 0.9. And if p hat is 0.9, that leaves 0.10 left over for q. The confidence level that we're looking for here is 99%, or 0.99. Which leaves 1%, or 0.01, left over for alpha, or 0.005 for alpha over 2. This time, let's use our calculators to construct this confidence interval. To locate the 1PROP-Z-INT function, we first go into the Stat menu and toggle over to Tests. Then scroll down to option A, 1PROP-Z-INT. Be careful to notice that the X value is the number of people, not the sample proportion. We calculated X to be 468. Our sample size in this case is 520, and the confidence level that we are interested in is 99%. Notice that the output gives us the interval along with the sample proportion and the sample size. So our interval, rounding to 2 decimal places, is 0.87 to 0.93. In our calculators, we use the function 1PROP-Z-INT, and we entered our values for X, N, and the confidence level. Those were 468, 520, and 99%, or 0.99. We found a confidence interval of 0.87 to 0.93 if we round to 2 decimal places. This is equivalent to saying that we believe that the population proportion P is somewhere between 87% and 93%. To state these results in a complete sentence, we might write something like this. We are 99% confident that the interval 0.87 to 0.93 contains the actual population proportion. Now let's repeat this same process and instead use a confidence level of 80%. Most of our values will be the same. N is still 520, P hat is still 0.90, Q hat is still 0.10, but our confidence level is changing to 80%, or 0.80. That leaves 20%, or 0.20, left over for alpha, and alpha over 2 then becomes 0.10. Let's use our calculator again to calculate this confidence interval. Starting with the 1PROP-Z-INT function, we still have X is 468 and N is 520, but we'll change our confidence level to 0.80. And when we calculate the interval this time, we find the range of values is from 0.88 to 0.92. In other words, this time, we believe that the population proportion is between 0.88, or 88%, and 0.92, 92%. The last thing we'll do with this example is compare the 2 confidence intervals that we just calculated. Our 99% confidence interval was 0.87 to 0.93. Our 80% confidence interval was 0.88 to 0.92. Let's draw these on a quick number line to help us compare. Our sample proportion, P hat, is 90%, or 0.90, and our 99% confidence interval goes from 0.87 to 0.93, In other words, we are 99% confident that the actual population proportion is somewhere in this range. Our 80% confidence interval, on the other hand, goes from 0.88 to 0.92. In other words, we are 80% confident that the actual population proportion is in this range. The smaller the range of values, the less certain we are that we've captured the actual population proportion. The wider of a net that we cast, the more confident we can be that we will actually include the population proportion. That concludes this lecture video on estimating a population proportion by constructing a confidence interval estimate.